Hello everybody and welcome to a new Open Class. Today we are in Open Class number 202 and we are going to continue with the series that we started last week. We are going to be working with the BotBox, but today we are going to put the focus on how do robots move. Yeah. In last class we focused on how do robots perceive the world. And for today, we are going to focus on how robots move. All right, and for that, we are going to use the BotBox, which we introduced already last week. So yeah, hello everybody. Welcome to a new Open Class. Please let me know, as always, if everything is good, if the sound is good, the image is also good. I'm going to be checking the chat to see your feedback. So yeah, without any more delay, let's get started. So I'm going to switch already to my computer screen so that I can start opening the class and checking your messages. Let me go to the class. There we are. Okay. Hello, Krish, Araf, Anushka, Saifani says everything is good. Also Krish, everything good, perfect. All right, excellent. Then let's get started. As always, for this class, I have prepared a project. Okay, so it is very important that you get a copy of this project. A project basically is a self-contained project with everything installed, so you don't have to worry about anything. The whole environment is prepared for you to just start developing. Yeah. Then, in case that you are new to these open classes, let me tell you that to get a copy of this project, all you have to do is to click on the button that it's going to you're going to find here right above the chat box. This button here which says fork and open the class project. I'm going to click here myself also to get my own copy, which I'm going to use for today's class. So yeah, please go ahead and click on this button so that you get your very own copy of the project. And once you click on this button, a couple of things are going to happen. First of all, as you can see, you are going to be redirected here to the main project page, which is this one. Okay, here in the right side, you are going to find the streaming panel, let's say, with the chat, also the video feed and everything. In my case, I'm going to move this to another window so that I can have some more space for my project. And this is the main project area, let's say. It's going to take a few seconds to load. As you can see, mine here is still loading. And once it finishes loading, it should show you, not all these, but it should show you the notebook, the Jupyter notebook, automatically opened here and loaded with the contents of today's class. Yeah, as you can see, this is class number 202, how robots move. All right. Let me go back here to the Open Class page so that I can see your messages. Hello, everybody. Then, besides this, besides being redirected to the main project page, which we are going to start working here in a moment, let me also explain that by clicking on this button here, you are also creating a permanent copy of this project into your account. Yeah. And you can access this copy whenever you want, just by coming here to the left side menu and going to the My Projects section, which you can find here, My Projects. Then if you click here, here is where you are going to have all your projects. And in this case, here is where you are going to find the copy of this project that I have prepared for today's class. Yeah. So this project is not only for today's class, but you can open it again tomorrow, next week, next month, whenever you want to continue working on it. All right. Then let me know, has everybody opened the project already? Are we ready to get started with the class? Any issues so far? Hello, Omar, Juan, Lucas, Michael, Ali. Aman says ready. Jairo says that the notebook is still loading. Okay, don't worry, just be patient. All is fine, says Gilbert. Still loading, all fine. Okay, so if it's still loading, don't worry, in a few seconds it's going to finish loading, so no problem with that, okay? The important thing is that everybody has been able to get his copy of the ROSJECT. Then, today's class, we are going to talk about how robots move, okay? Then, for this class, we are going to be using, again, the BotBox, yeah? If you attended to the last class, probably you are already familiar, but basically the BotBox is a all-in-one classroom robot kit for teaching or for doing your own personal projects, which includes a real robotics lab, which you can see right here, already mounted, robotics courses, and practical projects to practice with, all right? It's this box that you can see here already mounted. And it is designed to provide hands-on practice-based robotics classes with minimal preparation and maintenance. It is easy to assemble and can be used in various real-world teaching scenarios. Here you can see it on a university that we delivered few days ago. And yeah, it's very easy, as you can see, it's very easy to assemble, and you can put it almost everywhere, okay? It doesn't take that much space, and it's perfect for teaching robotics, both in a simulation and with a real-world environment, yeah? This is what the package includes, yeah? With the 3 robots, all the environment to be mounted, cubes with QR codes, also to practice perception, to practice grasping. It also includes 3 grippers for the robots, so that you can also practice manipulation stuff. It provides already made projects, so that you can practice navigation, perception, basics like topics, services, etc. All this provided, and also a students management panel, okay? So if you want to learn more about this BotBox, you can go to this link here and get more details about the BotBox, yeah? Or even order one in case that you are interested. All right, then having properly introduced the BotBox, which is the environment that we are going to be using for today's class, let's get into the topic, which is how robots move, yeah? There are different methods of robots to move, and it is very important, yeah? The way in which a robot moves is going to basically define the robot, and it's going to define what is the purpose of that robot, yeah? Then let's introduce some of the more common ones, starting by the most common one, which is probably the wheeled movement, yeah? Wheeled robots are among the most common and widely used types of robots, okay? They are simple, affordable, they provide speed, efficiency, yeah? And they can be used for many different tasks. Now, inside the wheeled movement, there are also some different types of movement. The differential drive, okay, which is probably the simplest one or the most common one, the ones that the most basic, let's say, robots use. There is also tricycle drive or omnidirectional wheels, which provides movement in every direction, okay? For the case of the BotBox, which is the one that we are going to be using today, it uses a differential drive, okay? I will show you in a moment. Does everybody understand, for instance, the difference between differential drive and omnidirectional movement? I think this is pretty straightforward, but I want to make sure. Yes. Jairo says that the notebook is still loading. Okay, maybe try closing it and open it again or something like that. Jairo. Yes, okay, so I see that this is This is understood by everybody. Aman says, Omni is the type that can also strafe right. Strafe, yes. I'm not sure what you mean by a strafe, but yeah, basically omnidirectional wheels allow you to move in the y-axis, for instance, without the need of rotating the robot. Okay? All right, another very well-known type of movement is the legged movement. Yeah? This is used, for instance, by humanoid robots. Yeah? A legged movement allows a robot to move, for instance, like a human or like an animal. Yeah? This would be the case of the quadrupedal robots. Okay? Also very well known lately with some of the robots that have been appearing. Yeah? And besides, there's also more complex ones like hexapods and beyond. Okay? But this is also a very typical movement for robots, which is using legs. Yeah. Another one is a tracked movement. Yeah. Tracked robots are used usually in more rough environments, rough and uneven environments. Yeah, I'm thinking, for instance, in exterior environments, mountain-like environments. Yeah. A good example would be, for instance, the Mars rovers robot from NASA, yeah, which is used in Mars, which is a rough and uneven environment, yeah, and in this case, the purpose of this robot would be exploration, yeah, but it can also they can also be useful in other environments such as construction, demolition, etc. Yeah, and finally, a very well-known movement is the aerial movement. Yeah, you can think of quadcopters or even winged drones. Yeah, so as you can see, there are different types of movements which robots can use, and it is something very important when you design a robot. Yeah, basically, it's crucial. Yeah, because it's going to completely define the robot itself, but also it's going to define the purpose of the robot. Yeah, depending on the purpose or the goal you want to achieve with that robot, you are going to select one type of movement or another. Yeah. Then, for the BotBox, as I already said, it uses a wheeled movement, and more specifically, it uses a differential drive type of motion. Okay. Now, let's start exploring a little bit this movement with the BotBox by starting a simulation of this robot, okay? Then, in order to launch the simulation, all you have to do is to execute these commands here. First, we need to source this specific ROS to workspace, and then we execute a ROS to launch command to start the simulation, okay? Now, in order to be able to execute these commands, what we need is a terminal, right? So how to start a new terminal? Very easy. We go here to the bottom bar here. You are going to find this menu with different buttons. And we are going to click, in this case, in the very first icon here, which says Web Shell. Yeah? If you click here, it is going to automatically open here a new blank terminal. This is a Linux terminal where you can execute commands. Yeah, and in this case, we want to execute these two, so the easiest way to do it is to just select the commands, copy them from the notebook, like this, and then go back to the terminal and paste them, okay? Then you press Enter to execute the ROS to launch command, and the simulation processes are going to automatically start here. And after a few seconds, as you can see here in my screen, the simulation should automatically appear here in the ROSJECT, okay? You can make it bigger to have a better look of it. Yeah? So everybody, let's go ahead and execute, and let's just start the simulation, all right? Okay. Now, as you can see, in this environment, we have different areas. Okay, this is actually a simplified version of the warehouse environment that the BotBox provides. Okay, but you can see here different rooms, different areas with some corridors, some objects on the different rooms. Yeah, so all this is going to obviously condition where the robot can move and where it cannot move. Yeah, so in order for the robot to be able to successfully avoid crashing against the walls or crashing against the obstacles, we need to provide some kind of assistance to its movement. For instance, we need to create some kind of obstacle avoidance algorithm. Yeah. So this is the very next thing that we are going to do. Yeah, we are going to create from scratch a ROS2 program so that the robot can autonomously avoid any obstacles that it finds on its way. Yeah, and in order to be able to do so, we are going to make use of the wheels, obviously, to move the robot, and also the laser scanner. Yeah, so that the robot is able to detect any object that it's in its surroundings. Yeah, so we are going to combine a little bit what we learned during the last class, which was how robots perceive the world. In this case, this robot, we are going to make it perceive the world using its laser sensor, and also how robots move, in this case, using the wheels and the differential drive motion that the BotBox provides. Yeah? But for this, the very first thing we need to do is to launch the simulation. Yeah? Are we good? Let me have a quick look here at the comments. Aman says, yes, I meant A-axis movement. Thank you for the clarification. All right. Yes, yes, yes. Okay, excellent. Then let's continue. All right. So the very first thing that we can do is to try to move a little bit the robot using the basic Teleop twist keyboard program. Yeah, this is a program which is provided by default by ROS2, and this program allows you to basically control the movement of the robot, send velocities to the robot using your keyboard. Yeah. So let's try to execute this command. For this, let's go back to the terminal. All right, and we are going to leave this one here running, because in this terminal is where we have the simulation basically running, so we don't want to close it, because otherwise the simulation would stop. Then what we are going to do is to open a second terminal, so that we can continue executing commands without affecting the simulation. So for this, let's just click here in this plus icon, which says Create New Terminal. Let me click here myself, and as you can see, this basically opens a second terminal where we can continue executing commands without affecting the simulation, right? Then, in this second terminal, we can copy and paste this command. Let's do it. There we go. And now, using the keyboard, yeah, you can see here exactly the keys for moving around, yeah? For instance, the A key is to move forward, the J key is to rotate to the left, the L key is to rotate to the right, the K key is to stop the robot, etc. Okay? Then, keeping the focus of the prompt in this terminal, we can start pressing the keys in our keyboard, and as you are going to see in the simulation, the robot is going to start moving. So you can see right now how my robot is moving forward. Now I just stop the robot. I'm going to start rotating to the left now. There we go. Yeah. So basically here I am sending velocities to the robot. Yeah. So I am moving my BotBox using the keyboard. Okay. And as you can see, this is basically a differential drive motion. Yeah. So I can move alongside the x-axis, which means basically forward, as you can see, and also backward. But if I want to move through the y-axis, I need to first rotate the robot, as you can see, yeah? I need to rotate the robot, and then I can start moving alongside the y-axis, which becomes now the x-axis of the robot. Yeah. So this is basically the characteristics of a differential drive motion. All right. In case, for instance, of an omnidirectional robot, I would be able to move alongside the y-axis without the need of rotating. Yeah? That would be for an omnidirectional motion. Yeah? Okay, so is everybody able to move the robot in the simulation? My robot doesn't appear on the map, says Aman. Fix it. Okay, excellent. In case that you have some problems with the simulation, yeah, like the robot is not appearing, maybe for whatever reason you are not being able to move the robot, okay, don't worry. In case you have any problem, what you should do is to go back to the terminal where you have the simulation running, then press Ctrl+C to stop it, to stop the simulation, okay? And then you have to follow the instructions which are here in the notebook, in the red notes, here, right below the simulation image. Yeah. So stop the current simulation by pressing Ctrl+C in the terminal where you launched the simulation, step number 1. Step number 2 is to stop all Gazebo processes by executing the following script, okay? So you execute this script here to make sure that the Gazebo is properly killed, okay? So let me do this. As you can see now, Gazebo is properly killed. And then final step is to just execute again the simulation bring up command to start the simulation, okay? And then after restarting it, it should work properly, all right? So here I have again my simulation, and let me execute one more time the keyboard teleop program to make sure that I can move my robot properly. There we go. Okay? Yeah. All right, so we can see now that our robot moves properly, and it uses a differential drive motion. It is obviously a wheeled robot, yeah, with 2 wheels here and a caster wheel to provide support. Here in the back part, yeah, here we can see the caster wheel. All right. Then go back here. All right. Then let's do a practical example, which would be to create an obstacle avoidance algorithm using laser data. Yeah. So you can see here in blue, in the top part of the robot, we have a LiDAR sensor. Yeah. So we are going to use this laser data, combine it with the wheel motion in order to create a program that makes the robot move around the environment while avoiding obstacles. Okay? Then for this, we are going to start by creating a new ROS2 package inside our ROS2 workspace. Okay? At this point, before starting to work with the code, what I recommend to you is that you open the code editor. Okay? Then in order to open the code editor, you have to go again back here to the bottom menu, and in this case, select the second icon, which says code editor. I'm going to click here myself, and this is going to open the code editor in another window. And this is basically going to allow you to have a graphical interface for visualizing your packages, your programs, editing the code, etc. Yeah? In this case, we are going to be working inside the ROS2 workspace, which right now it's empty. But then let's go back to the notebook and let's follow the instructions here in order to first go inside the source folder of the ROS2 workspace. Let me do this, for instance, here in the second terminal. And then I'm going to execute the second command, ROS2 package create, to create a new ROS2 package. Okay, as you can see, the name of the package is obstacle avoidance. Yeah? Obstacle avoidance. Now, if you go back to the code editor, you are going to see that the new ROS2 package has been created here inside the source folder of the ROS2 workspace. Right? Okay, and then the next step is to create our Python script. Okay, we are going to create our program in Python. So this is the name that we are going to give to our script. So let me copy it here. And then I'm going to go inside the obstacle avoidance folder here, and then right-click, new file, and set the name of the file, yeah, which is laserobstacleavoidance.py. Click OK, and then you're going to see the new Python script appearing here also. And right now, as you can see, it's empty because we have just created the file, right? Then, in order to create this obstacle avoidance algorithm, what do we need? Well, we need basically two steps. First of all, we need to be able to read the laser scan data, right? Then how can we achieve this in ROS? Well, this is done through a subscriber, yeah? If we want to read the data from the laser, what we need to do is to create a subscriber for the topic where the laser is publishing its data. And what is this topic? This topic is scan. Yeah? In the previous class, we already saw how to visualize properly this laser data, so I'm not going to go again over this. Yeah? So basically, if you want to read the laser data, what you have to do is to create a subscriber for the laser topic, which in this case is this scan topic. All right? And then, obviously, every subscriber in ROS has an associated callback method. Okay? This is step number one. Now, once we have access to the laser scan data, step number two is to analyze this laser data, process it, and based it on the readings, decide how to move the robot, right? This is what we are doing in step number two. So here what we do are two things. First of all, we have to create a publisher, yeah? A publisher so that we can publish velocities for the robot to move, yeah? And velocities are published in the command bell topic. Yeah, this is a very standard topic in ROS, CMD bell, command bell, which is used to send velocities, yeah, command velocities to the robot. So we need to create a publisher so that we can publish velocities to the robot in order to move it, yeah? And then here inside the laser callback, what we do is to get the laser readings, analyze them. Yeah, in this case, we are analyzing the data from the front of the laser, yeah, and create some kind of logic for obstacle avoidance. The logic that we are applying here is very simple, yeah. So we set a threshold distance of 0.5 meters, okay, and then we say that if the front distance of the laser readings is lower than this threshold of 0.5, we are going to rotate the robot, yeah? Otherwise, we are going to keep moving the robot forward, yeah? So basically, what this algorithm is going to do is to move the robot forward until the front data from the laser detects an obstacle closer than 0.5 meters, yeah? If it detects an obstacle closer than this threshold distance, then the robot is going to stop moving forward and start rotating. As we can see here, yeah? Very basic if-else algorithm. All right? So the final program is going to look something like this, with everything combined, yeah? We have our class with the constructor where we declare our subscriber and our publisher, and then we have the laser callback here with the logic. And finally, a main function where we initialize our node. Yeah? Okay, then let's copy this code, the complete code that we have here. Let's copy the whole code and paste it into our script using the code editor. There we go. So now I have populated my Python script here. And then next step is to update the setup.py file. Yeah? In ROS2 Python packages, which is this case, yeah, this obstacle avoidance is a Python-based package, we have to edit the setup.py file in order to generate executables from our programs, yeah? This is basically what we are doing here in the entry points. So you can directly copy this section here, the entry points, and replace the one that you have here. There you go, yeah? Then here we are generating this executable file from the laser obstacle avoidance Python script. Yeah, the entry point in this case is the main function. And then finally, after you have properly updated the setup.py, the final step is to build the package. Yeah. So let's go to the root of the workspace, which is here ROS2 workspace, and then execute callcon build in order to compile our obstacle avoidance package. Yeah. And then after some seconds, when the build process finishes, we can source the workspace. There we go. And we are ready to execute our program with the following command. So ROS2 run, obstacle avoidance, name of the package, and name of the executable that we have just created. And then let me put the simulation here so that I can see the actual behavior and execute the program. So now we are going to see the robot start moving forward. We should see that at least. There we go. It's moving forward. And at some moment, when it detects that this wall is closer than 0.5, the laser detects this, you can see that the robot starts rotating to avoid crashing against it. Yeah? So the readings that we are monitoring are the ones of the front of the laser. Yeah? So every time the front laser detects an obstacle, which is closer than the threshold distance, the robot starts rotating in order to avoid it. And whenever there is no obstacle detected, at least as close as the threshold distance, the robot keeps moving forward. Yeah? So here, for instance, it's detecting this wall. So it keeps rotating. Now, at some point here, it's not going to detect anything because there is this opening here. So the robot is going to keep moving and is going to skip the room because there is no detection in the front direction of the robot, yeah, because of this opening. So now the robot is going to keep moving continuously, okay? Then let me stop here my program already. Yeah? Does it make sense? Have you been able to create your package, execute it, etc.? Let me have a look here at the comments. Fix it, fix it. Yeah, if you are getting this error, Jairo, package not found, then probably the solution is what Krish is commenting here. You need to source the workspace. The obstacle detection is working, says Jacob. Awesome. Aman says, third line in scan callback. Could you explain how you know what part of LiDAR is front section? That is a very good question. Aman, this is a very good question. So here in the program, we are in the scan callback, as you can see. Yeah. What we are doing is to get the values of the front of the laser, yeah, of the front of the robot, let's say. Then, in this case, these values are inside a specific region of the ranges array, okay? Let me very quickly explain this because, well, actually for this I need to restart the simulation. So let me very quickly restart it. There we go. Then ROS to topic echo scan. Okay, so I'm going to create a runtime subscriber of the scan topic, and this is going to allow me to start receiving here in the terminal the commands published into the scan topic. Okay. There we go. Okay. Then, how does a laser message look like? Okay. Well, it basically has three, main parts. Let's say that for this example, we are going to say two. First of all, it has the header, which contains some information related to the message. For instance, the minimum angle of increment from one laser beam to another, the maximum. No, this is the angle increment, sorry. And this says where the beams start and where they end. Okay? So in this case, it's 0 radians and 6.28 radians. Okay? And this is the increment, the angle increment between the minimum and the maximum. Yeah? So dividing this by this, we would have, for instance, the total number of laser beams. Okay? Then here we have the minimum range of the laser beam, the maximum range, which is 20 meters in this case. And then we have an array of ranges. Yeah? These are all the individual values of each beam. Okay? What does this mean? This means that each of these values corresponds to a specific angle. Okay? In this case, this laser has a scope, as you can see, of 360 degrees. Yeah? So it covers an area which is a circle all around the robot. Okay? Then, for this specific case, we know that the 0 is here. Yeah? Then the front of the laser is going to be from the reading 0 to 10 and from 0 to minus 10. Yeah? So considering that 0 is exactly the front, we are getting 10 readings to the left and 10 readings to the right. And we are considering all this area as the front area of the robot. Okay? Now, this can be done by testing, for instance. Through testing, you can create a script and do error test. You can do the mathematical calculations also using this information from the message. Yeah, like the angle mean, angle max, angle increment, etc. Okay? And this changes from one laser to another. Yeah? In fact, we are going to see how this is different later. Okay? In some minutes, I'm going to connect to a real robot, and you are going to see how this information is different for the real laser. Okay? Because the configuration of the laser is different. Yeah? Does it make sense? Does this answer the question? Thank you. This makes so much sense now. Okay. Great, Aman, great. My code editor shows errors, says Omar. Okay. Probably you had some error when copy pasting. Okay. Try removing your code and try copying and pasting by selecting the whole code. Okay. Instead of using this copy button, try just selecting the code and then copying it like this. Okay. If you do it like this, it should work properly. Okay. Yeah. Obstacle avoidance, laser obstacle avoidance. Line 33. I don't know, Jayanta. I will need to see exactly what you are doing here, okay? Let me quickly try to go over the step by step, okay? Very quickly. I cannot stop a lot of time because otherwise we cannot advance, but basically everything is step by step explained in the notebook, okay? Everything that I am doing is explained step by step in the notebook, okay? So, in case that you are getting some errors, just don't worry, go back and have a look at the notebook, okay? Here everything is explained step by step. So step number 1 is to create the package with the following commands, okay? This is going to create your package here inside ROS2 Workspace SRC, okay? Then, inside the second obstacle avoidance folder, yeah, the first one is the main package, second one obstacle avoidance folder, here, inside here, alongside this init.py file, you have to create, this is already created by default when you create the package, you have to create this Python script, laser obstacle avoidance.py, okay? Then, inside this file, you paste the code that appears here, laser obstacle avoidance.py, okay? You just have to copy and paste the code that appears here, yeah? And then you have to edit the entry points section in your setup.py here, yeah? So inside your package, you are going to find this setup.py file, and then you have to edit this entry points section here, okay? Yeah, as you can see, in the default one, you are not going to have this line. So what you need to do is to copy the entry points section here from the notebook and paste it here. You can just replace the whole section. Sorry. Do it like this, Control B. And here I am missing something. There we go. Oh no, sorry. Okay, now. There we go. Okay? And then once you have all this done, all you have to do is to go back to the ROS2 workspace and compile. Okay? If you follow these steps properly, it's going to build correctly. Okay? If it doesn't build correctly, then review one of these steps because you have done something wrong or you have missed some of the steps. All right? Jacob says, I had to delete hidden spaces that came from copying it in new lines. You can just remove the added space and it should work. Yes. So this is an issue that sometimes happens, which is that if you copy the code using this button here, then some spaces or weird characters can be added in the copy-paste process. Yeah. This is why I recommend you to just copy and paste by selecting the code here, like this. Okay. Without using this button. Yeah? Okay, don't worry, Jairo. All right, then let's continue. Now, here we have created a very basic, very simple obstacle avoidance algorithm, okay? Now, there are much more complex ways of controlling the movement of a robot, yeah? For instance, here I want to show you a navigation system that can be used with the BotBox in this case, but with basically any robot, yeah? Which is a much more complex method of controlling a robot's movement while also implementing obstacle avoidance. Then, for this, I have already prepared the files, okay? You don't need to create any files. All the files are already here in the BotBox nav workspace. You can have a look if you want here. So you don't have to create anything. All you have to do here is to execute these commands, okay? So first we execute the source of the BotBox navigation workspace, like this. And then second, you launch the navigation system with this second command. ROS to launch, path planner server, single main, etc. Yeah? So let's do this. And then this is going to start the whole navigation system, okay? Then we are going to see also automatically appearing here a window with RVs. There we go. With a configuration. There we have RVs, yeah? So this is RVs, which by the way also we were using in the last class and configuring it a little bit. Here, as you can see, it already loads a pre-configured file for RVs, yeah? And here, basically, what we can see is a map of the warehouse environment, yeah? If I change the simulation here and I go to a top view, you are going to see how the environment matches perfectly this map. Sorry, let me zoom out a little bit, yeah? So you can see here how this environment, yeah, matches the map, yeah? This is because navigation works with maps of the environment, yeah? You can also see here in red the readings from the laser, which is in fact detecting the walls of this room, yeah? And there are also some more complex aspects such as cost maps, etc. But I'm not going to go into all those details because that would be too much. Maybe in another class, okay? But basically, here, what I want to show you is a navigation system already working, yeah? And how does a navigation system work? Well, basically, here you can send goals to the robot, yeah? Here we can see the robot, and then by using the 2D goal pose button, which you can find here, okay? In the top area of RVs, you are going to find one button which is 2D goal pose, yeah? Then by clicking on this button and then drag and dropping it in some point of the map, for instance, here I'm going to put it here in front of the robot. I click here and then I drag and drop, also setting the direction. This is sending a goal for the robot, yeah? And the robot is going to start moving towards that goal, okay? Let me send it again because it looks like it didn't get the goal properly. Or maybe, I think there is something wrong in my simulation, in my Gazebo, yeah. So let me just relaunch the simulation because here the time is not passing in the simulation, so probably something crashed here in the simulation. Yeah, here I can see. Then let me just restart the simulation. There we go. Let me restart the simulation and then also restart the navigation system. There we go. Okay. Let's wait a little bit until this fully loads. And then, there we go. There we go. Okay. Yeah. So now, what I'm going to do here, what a navigation system, a fully working navigation system allows me to do, is to send goals to the robot. Yeah? Then, for instance, I'm going to send a goal here in front of the robot, inside the map, of course, and then the robot is going to generate a path, which can be seen here also in green, and you can see that the robot starts autonomously navigating towards this goal point, which I have set here. Yeah? Then this is a much more complex system than the simple obstacle avoidance behavior that we created, okay? You can try also sending other goals. Like for instance, let me try to send a goal here in that direction. And you can see here in green how a path is computed, yeah? And then in this case here, the robot is rotating and it's going to try to navigate towards that goal. Yeah, here it is rotating and it's going to try to move through this corridor in order to reach the end goal. Yeah, there can be some problems depending on the configuration. Yeah, but here so far it's succeeding, it's gone past the corridor, and it's almost reaching the goal point here. Yeah? Then this is another way of motion, which is much more complex in different ways. Yeah. So what does this navigation system provide? First of all, path planning. Yeah. So when you set a goal for your robot, there are certain algorithms which can be changed. For instance, typical ones are A star or Jigstra. Okay, but there are others that can be used. Yeah. So the system uses algorithms, well-known navigation algorithms, in order to compute a safe path from the current robot position to the goal position. Yeah? Also, the navigation system is in charge of sending the velocities to the robot so that this path can be properly executed by the robot. Yeah? But also, while this path is being executed, yeah, there is obstacle avoidance being used by means of laser data. Yeah? So the system takes into account the laser data, and it avoids static objects like the walls, but also dynamic objects that might appear and that are not in the map. Okay? Yeah? So, yeah, just wanted to show you here a demonstration of a much more complex obstacle avoidance system, which is by using the navigation to stack. Okay. Nothing happens with the robot. Try to restart the simulation, Lucas, like I did. Okay. And Jayanta also solved the problem. Excellent. Excellent. Okay. Yeah. Can you make a set of goals? Yes, Aman. You can create a program where you put several goals. You can send goals from a program. Yeah. Here I am using RVs in order to send goals, but usually these goals are going to be sent through a program. Okay. Then yes, you can concatenate as many goals as you want, create a specific paths, many things. Okay. So the navigation to framework is super powerful, and it allows for a lot of cool things. A lot of customization and a lot of complex robotic behaviors, okay? All right. Then, at this point, let me already stop the simulation because I want to very quickly switch to the real robot. Okay, so I'm going to stop the navigation system here, and I'm going to stop also the simulation. And I want to do a very quick real robot connection, as I did in the last class. If you remember, we have 5 minutes left until the class end. So I want to test the first algorithm that we have created, this one with the laser obstacle avoidance, with a real environment, okay? Because a very cool feature that the BotBox provides is that you can test programs. You can test your projects, or you can test your teaching lessons, both in a simulated environment, like we have done, but seamlessly you can move from a simulated environment to a real robot, okay? Here, I'm going to connect to my BotBox environment, to my real BotBox environment, just by clicking here on this button in the ROSJECT. All right, so let me turn on the real robot connection. And just with one click, I'm going to switch from the simulated environment to the real robot environment. Everything here without moving outside the ROSJECT. All right? So now in a few seconds, you are going to see here the cameras appear. And I'm going to be already connected to a real BotBox robot. There we go. Here I have the cameras loading, and here I can see the sorry. Here I can see the real BotBox environment that I have mounted here in the construct offices, okay, with the robot here. And right now I am connected to this robot, so I can control it already, yeah? Let me open a new shell to demonstrate you this. Okay, I think the robot is already started. Yep. Then here I can already execute, for instance, a ROS to topic list. And I should be able to see the real robot topics. Here I can see command bell, scan, for instance. Yeah. So I can, of course, also run the teleop keyboard in order to send velocities to the robot. And I'm going to be able to directly control the real robot here from the keyboard, as you can see, yeah? So let me, for instance, rotate it a little bit. I'm going to put it facing this wall to the left, yeah? Move forward a little bit, there we go, yeah? So right now I'm controlling the real robot already from the ROSJECT, yeah? So what do I want to test now? What I want is to test the program that we have created, this laser obstacle avoidance, with the real robot, okay? Because this is a highly valuable knowledge to acquire, which is that working with simulations, it's not the same as working with real robots and working in the real world, yeah? There are always things that need to be considered and that you need to take into consideration, yeah? So, can I use this program with a real robot? Yes, but I need to do some small modifications, okay? Not very big. I'm going to show you right now. So the very first modification that I need to do is related to the scan topic, yeah? So in my real robot, the laser, which is mounted, it has a specific QoS settings, okay? Which is very typical in real robots, yeah? So the laser has a QoS setting specifically for the reliability, which is set to best effort, okay? This is a more advanced ROS2 concept. I'm not going to get into too much detail, but yeah, this is something that you need to take into account and which usually can have different configurations for simulations and for real robots, yeah? So in this case, if I try to subscribe to the scan topic like this, I'm not going to be able to do so, yeah, because of this QoS profile, yeah? This is something that I already showed in the previous class also, yeah? Then, if I want to subscribe to the topic, I need to update the code with this, yeah? Then I'm going to add, first of all, an import of the QoS profile here to my program, and then I'm going to add this specific QoS configuration to my subscriber, just like this, okay? Now, second thing is with the process of the laser data, yeah? So, in the simulation, I was analyzing the positions from -10 to 10 from the ranges array, yeah? So, for the real robot, this is different, yeah? For the real robot, the positions that correspond to the front of the robot are actually 365, yeah? 365 is exactly the front of the robot, yeah? It's exactly the front of the robot, which in this case, it's this direction here, yeah? And this is because of the specific configuration of the laser that I have mounted on this real robot, yeah? So this changes from the real robot to the simulated version, yeah? Then instead of analyzing the 0 position, yeah, for the real robot, the front beam corresponds to the 365 position of the array, yeah? So then I need to update this, which I'm going to do right now. Let me comment out this, sorry. Comment out this here, and then add right here the new line, which, by the way, there is another thing that I am doing here. Yeah? I am filtering out values which are 0.0, because with real laser, sometimes there are some error readings which come through, which show a 0.0 value. Yeah? So for the real robot also, I am filtering out values which are 0.0. So I am only taking into consideration values which are higher than 0.0. Yeah? And then for the front distance, I'm going to get the minimum value with the following line. Okay? Yeah? And then one last point, which also it's advisable to always take into account, is that I'm going to reduce the speeds for the real robot. Yeah? So I'm going to reduce the angular velocity to 0.25 here, and the linear velocity to 0.1. Okay? Just to be safer. Okay? Then with these modifications already, I'm going to recompile the program. Let me do that right now. Colcon build. Source. And actually, let me do something else. Okay, I want to do something else, which is to add a very dirty print here, so that we can monitor the front distance value. Yeah, because we are keeping the threshold at 0.5, so printing here the front distance is going to allow us to clearly see what the program is doing, right? So let me recompile my program again. Then let me bring here to the front the camera so that I can see the real robot environment. There we go. Then source install setup.bash. And then I'm going to run the program, obstacle avoidance, and laser. There we go. Okay, so now my robot, as you can see, starts moving forward, and when this value goes below 0.5, the robot is going to stop and start rotating. Again, once it detects, once the front laser reading goes below 0.5, the robot stops and starts rotating to avoid the obstacle. If it's higher than 0.5, the robot keeps moving forward. Yeah? So right now, it's going to keep moving forward until it gets close enough to this wall here, and then it's going to start rotating in order to avoid it. Yeah? So as you can see, with some considerations, we can use the program that we created for the simulation into the real robot environment. Yeah? And as you can see, it works very well. Yeah? So this is a great way of practicing concepts such as obstacle avoidance, both in a simulated environment and in a real robot. Okay? You can see here how it's constantly avoiding the walls. Yeah? So let me already stop here. I'm going to stop the robot by publishing a 0 velocity. Stop it here, or actually let me stop it by running the, there we go. All right, let me bring it back to the center. There we go. All right. So yeah, unfortunately, this part of the class, working with the real robot, you cannot test it yourself, but I wanted to show you this also to demonstrate how easy it is with BotBox to switch from a simulated environment to a real robot environment in order to test and practice all these robotics concepts. So yeah, any questions, any final questions before we finish the class? Any comments? Aman says, wonderful session. Many thanks, Aman. So thanks for attending and for sharing your thoughts and being active throughout the class. I use a SlamTech RP LiDAR, as I so have to see the range for that too. Yes, exactly. So you will need to see how that specific laser is configured. Yeah, what is the the minimum range, maximum range, angle increment, etc. So all this information you can look it for that specific laser model. How to use voice commands to move robot in Jazzy? Is asking Say. Well, that's a complete different topic and very different, but it can be done. It can be done, but it's not possible to cover it in this class, unfortunately, Sai. But maybe we are going to do another class focused on that topic. It's also very interesting, this voice to command topic. Is position more appropriate for a mobile robot? What do you mean by position? Is position more appropriate for a mobile robot? I don't get your question, Christian. Is it complex to send that set of goals to a robot? Not, Aman. If you want to see that, I suggest having a look at the simple Commander API. I'm going to write it here in the chat. Have a look at this, okay? Simple Commander API from the nav2, from nav2. Control by position instead of velocity. Well, that can be done, yeah. So you can create a controller where you send position goals, and that is translated into velocity. That can be done, yes. Christian. But is it more appropriate? It depends. It depends, Christian. So for instance, if you use the nav2 stack, like we have been doing here in the notebook, you are going to be sending position goals. Yeah? So you don't worry about the velocities because all that is already managed by the navigation to stack. So if you use navigation 2, whatever you only care about position goals. Okay? You don't care about velocities, really. Ali says, can the algorithms for navigation to reach a goal and avoid obstacle be done while also mapping the environment? Is there a library that can help with that? Yes. So you can do navigation while mapping the environment. Yeah, that can be done. Usually you are going to first create the map and then do navigation, but you can also do navigation while mapping an environment. That is also possible, yes. Does this package work in Jazzy? Yes, Sai. So navigation to stack works in Jazzy, and this package that we created, the obstacle avoidance package, is going to also work in Jazzy. Yes, no problem with that. All right, everyone. So I'm going to finish it here. Thanks a lot for attending this class, for being here with me. I hope that you enjoyed it. I hope that you have learned something new and that you can take something to practice. Please, I have also left in the notebook some possible exercise challenges that you can use in order to keep practicing with this project and with the obstacle avoidance and the robots movement topic. So give it a look. And yeah, let me say also that we are going to stop. We are going to have a pause of 2 weeks for the open classes. Okay? So next 2 weeks, we are not going to have open classes. Okay? We are going to come back with open classes after that, which is going to be, I don't remember now exactly the date. But yeah, basically, we are not going to have open classes during the following next 2 weeks. Okay? We will come back. We will continue and resume the open classes after 3 weeks. So just bear this in mind, okay? And yeah, hope you all have enjoy your Christmas holidays or your regular holidays, and see you soon. Until then, as always, keep pushing your robotics learning. Bye-bye.